Okay, folks, typically in math, there's a trade-off between teaching the material in the correct order as far as logical construction and making things as easy as you can for students who are learning new and difficult concepts sort of on the fly as you try to introduce these topics. We could technically have started our discussions of sine and cosine and trigonometry at this point right here, but I actually think it was good that we spent so much time on the unit circle and evaluating trig expressions before getting to defining the trig functions. So in this pre-work, we're going to look at defining the trig functions sine of x and cosine of x. And so to help us out, I have a demonstration that I've stolen from Daniel Minford. I found it, and I think it's a really, really helpful demonstration. So I'm going to go ahead and pull it up, but you should be able to click this link here too, and you ought to do this. This is a very tactile demonstration, and I think there's a lot to learn from it. So I'll click that link, and so should you. So here I've clicked that link. You'll notice the first time I click it, it may not pop up, so you may have to hit this refresh button, and it pulls up this demonstration right here. Let me scroll down slightly. Okay. It's a little busy at this point, so let's go ahead and turn off our cosine function. And we all know angles in both degrees and radians, but that gets a little cluttered, so let's turn off our angles in degrees. This is now a little bit easier to look at. What you see here is that we've got a couple different points that we could move, but I'm going to come over here to this point on the unit circle, and I'm going to click and drag it. So hopefully you can see me grabbing this this green dot and rotating it on unit circle. And let's go back to 0. Okay. So what we need to learn how to do is to take our knowledge of the unit circle and convert that into this traditional function that we have right here. One thing that I think is really valuable about this demonstration, something that I didn't have shown to me when I was learning this, that we can only do now with these sorts of animations, is how you to think of your domain axis when we go to talk about the function sine of x. So something I found really valuable is this ability to roll and unroll this picture here. So in blue, we have what will become our domain axes for the function sine of x until we get it laid out there. And so you can see that the values on the domain axis are the angles on the unit circle. Okay? This is kind of a trade-off. This is not a perfect demonstration. We are used to dividing up our circle into parts that look like pi over 12, but then we don't write the pi over 12. We just have pi over 6, pi over 4, pi over 3. We skip 5 pi over 12, and then we put pi over 2 on here. This does make the graph look a little bit busy, so you kind of have a choice, and you can decide how many parts of the unit circle you want to break this into. I think that you'll either find the pi over 6 helpful, or I prefer the pi over 12 because even though I don't want the 1 pi over 12 or the 5 pi over 12, the pi over 6, pi over 4, pi over 3, those are all three my unit circle angles in the first quadrant, and you have all of those unit circle angles. So please spend some time, even though we're gonna get to work with this here in just a moment, please spend some time just playing with this. This is a very tactile demonstration, and there is something to learn just by manipulating this expression here. Okay. So we want to define this function sine of x. We're in the process of defining the sine function here. And we want to define this function that's going to be on this f of x axis here. So this will be our independent axis. This will be our dependent axis. These are our x values, and these are our f of x values. And what we notice is that as, if we were to take, say, the independent coordinate, pi over 6, we're going to find its y value by finding the value of the sine of the angle pi over 6 on the unit circle. So what is the sine of pi over 6? It's 1/2, and so you'll see that this ordered pair, when we're at x equals pi over 6, we're at the ordered pair pi over 6 comma 1/2. You can see there's the number 1/2 right there on the range axis. And then we rotate up to the angle pi over 4. And this is a little bit harder to tell, but this is the angle pi over 4, and we are roughly at the y value of 0.707, and you can see that here. We continue rotating this to pi over 3, and at pi over 3. If we were to compute the sine of pi over 3, that's the square root of 3 over 2, which is, I believe, 0.8 something. And you see that that's reflected on the graph. So here we have the independent variable, pi over 3, and the dependent variable is the sine of pi over 3, which is the square root of 3 over 2, or about 0.8 something. And then you can see that when we rotate on the unit circle, we open up the angle. Notice you can actually see the size of the angle right here. We open up the angle, and there's the length of the angle right there. It's the same idea. We open up the angle to pi over 2. Our independent variable is now at pi over 2, and our dependent variable is now at 1. So we are getting the output values for this function. Notice that even though I've only discussed the nice unit circle angles, there's infinitely many values between 0 and pi over 2, and you can see that this, I don't know if this is blue or purple, line right here, this line right here is that collection of all those infinitely many ordered pairs. And so what we can see is that as you continue around one rotation of the unit circle, you trace out the graph of your function. This is the graph of the sine of x. So this is the graph that we want to get familiar with. We want to learn how to build it. But my reason for going through this demonstration really slowly is to show you the connection between what we've been doing on the unit circle and the graph of the function right here. So please play around with that. I want to point out one thing though. This demonstration, there's no perfect demonstration. This demonstration has to reset itself when we get to 2 pi and it starts over. In reality, this graph continues on off my screen as we go through successive rotations around our circle. So please take a few minutes to play with this, and I'll join you back on our pre-work page in a moment. Okay, so returning to our pre-work page, what we want to do now is we want to build that graph that we were just looking at. So the function, here we are ready to define it. The function f of x equals sine of x inputs real numbers from the entire real number line. So this is from minus infinity to infinity. And it outputs the ratio of the opposite side over the hypotenuse side of a triangle constructed from a reference angle on the unit circle corresponding to an angle of measure x. Now this is very important here, folks, because this can cause a great deal of confusion as we're learning all this. Here, instead of writing theta for the angle, I'm writing x. And so I'm going to refer to my angle as x. Here we can see the angle down here on the independent axis is listed as x, and the output value, or the y value, is the functional value sine of x here. That can cause some confusion. I'll highlight that one more time in a moment. So if I have, let's say we take the independent variable 0, when x is 0, we're going to compute the sine of 0. And the sine of 0, if you were to go to our unit circle and you were to plot that angle right there, there's the angle 0, that's the ordered pair 1, 0. And so when I go to compute the sine of 0, I want this coordinate right here. What is the sine of 0? It's 0. So there I'm going to plot the ordered pair 0, 0. And I want to do that for a whole bunch of points until I can start to imagine the shape of this function. Okay? So we could also do this when x is equal to pi over 6. We would be looking at the sine of pi over 6. And we know that the sine of pi over 6 is 1/2. So at the independent variable, pi over 6, we're going to go plot the ordered pair pi over 6, 1/2. So that would be this point right here. So this is the ordered pair. It's going to get a little messy. This is the ordered pair pi over 6, 1/2. And we can continue. When x is pi over 4, we'll be looking at the sine of pi over 4, which is the square root of 2 over 2. And so we have the ordered pair pi over 4, square root of 2 over 2, which is about 0.707. Let's go ahead and label that point. It's going to get a little messy. I think we'll put it down here. So there's the ordered pair pi over 4, square root of 2 over 2. Okay. What I'd like to do is let's bring back in that demonstration to just kind of reiterate how that's working with this. Let me see here. I think I want this one. Yes. So, I'm going to scroll down just a little bit here. So here you can see we're in the process of graphing this function, here we had, when x was 0, my angle here is 0, the output value was 0, so that gave us this ordered pair right here. Then I rotated up, let's see here, let's put ourselves into pi's over 12s. So then I rotated up to the angle pi over 6. When I'm at pi over 6, my sine value is 1/2. And so I plotted the ordered pair pi over 6, 1/2. That's this ordered pair right here. When x is pi over 4, my sine value is the square root of 2 over 2. So my angle, remember x does not, here, when I'm talking about x here, I'm not talking about on my unit circle, I'm talking about the independent variable that I'm plugging into the sine function. So x is playing the role of an angle here, not of the x coordinate on the unit circle. So when my angle is pi over 4, my output value for the sine is this number right here. That's the sine value, and so I plotted that point right there. That's about 0.707. It's exactly the square root of 2 over 2. And we continue on, and we're going to keep plotting these points. So when x is pi over 3, we're going to take, for the sine of pi over 3, we know that the sine of pi over 3 is the square root of 3 over 2. So there's the ordered pair. That's going to be the pi over 3, comma, square root of 2 over 2. And then when x is pi over 2, our output value is 1. And so there's the ordered pair, pi over 2, comma, 1. There's that ordered pair. Okay. We could continue on. For example, when x is 2 pi over 3, we're back up here. Let me go ahead and put a couple more tick marks on here. So if x were 2 pi over 3, that would be about right there, 2 pi over 3. And that would correspond to about this point right here. And when x is 5 pi over 4, we're about right here. And when x would be 5 pi over 6, we'd be up here at 1/2. And then when x were pi, let's just remind ourselves, if x were pi, let's see here, let's go over here. If x equals pi, the sine of pi is equal to 0. And so we're back down here at this point. If I were to start imagining all the points, because I only plotted the nice unit circle points, but if I were starting to imagine all of the angles between 0 and 2 pi, and I computed their sine value by finding the appropriate ratios, and I plotted them, that collection of points would start to look like this graph right here. Let's go ahead and point this out. If this were the angle 3 pi over 2, then we need to find the sine of 3 pi over 2. What is the sine of 3 pi over 2? Well, if you're not sure, draw yourself a quick little sketch of the unit circle. And the angle 3 pi over 2 is this angle right here. And those are the points, those would be the coordinates on the unit circle, 0, -1. And the sine value is that y coordinate, so that's -1. So we can go ahead and plot the ordered pair, 3 pi over 2, comma, -1. Okay. And when we get back to x is equal to 2 pi, the sine of 2 pi is 0. And I can now start to sketch the graph of this function right here. Now, one thing that I want you to try to avoid doing is notice here it looks like I'm coming vertically downwards, and that would not be a function if I were coming vertically downwards. So I really ought to, I'm gonna adjust this sketch. You don't have to if yours looks like this, but you want to try to avoid this part right here. You want to make sure that you're kind of coming in slightly at an angle and that you are not at a vertical angle when you cross through that axis. And this continues on because we can do this graph for infinitely many angles going to the right. We can also sketch this graph going to the left. We know, for instance, that this should have the ordered pair minus pi over 2, comma, -1. Why is that? Because the sine of minus pi over 2 is equal to -1. So this is our independent variable x. That should have been in a different color there, folks. This is our independent variable x, and this is its corresponding dependent variable, which is the sine of minus pi over 2. So again, folks, one thing that's really valuable to understand is the connection between the unit circle values on here and how we go ahead and construct the graph of the sine of x. Alrighty, folks, what I would like you to do now is, let me finish this out. So I want to finish this out by continuing on this graph, and it would look something like so. and continuing on with this graph. And it continues on forever in this direction as well. So we'll put arrows on here showing that the graph continues. And there is the graph of our sine of x function. Okay. What I would like you to do is I would like you to go ahead and try to graph the cosine of x here based on what we were just discussing, where you're going to say, okay, let me go ahead and take one of my unit circle angles. We could evaluate f of, say, pi over 6. Here would be the cosine of pi over 6, and the cosine of pi over 6 we know to be the square root of 3 over 2. And so these two, the angle, that should be in a different color, folks, the angle and the output become the ordered pair, pi over 6 comma square root of 3 over 2, and there's that ordered pair, pi over 6 comma square root of 3 over 2. So what I'd like you to do is, before you watch the next video, try to construct the graph of cosine on your own, and I'll see you in the next video.